Hello, welcome to Pre-Cal Lecture 4.4, where we are going to talk about the number e. So we have pre-printed notes for this one. Your notes cover 4.4 through 4.6. Today we're just going to really cover the first page and a little bit of the second page. And up here at the top you've got a blank area where we're going to draw a couple of graphs. So the number e. So it's a lowercase e, and I'm going to draw a few graphs here to help describe the graph of the number e. So this is the point 0, 1 right there. I moved it out of the way because I've got I didn't want it to be in the way of the graph, but the point 0, 1, and y equals e to the x looks something like this. All right, so just comparing it to previous lectures, it's steeper. It's a better way to put it. It's steeper than y equals 2 to the x, which we have graphed before, but it is not as steep as y equals 3 to the x. So it's in between those two. So let me draw a graph to the right up on your notes of just y equals e to the x. So here we are at the point 0, 1. So it crosses the y-axis at 1. It's an exponential looking graph. And the thing that makes it special is right when it crosses the y-axis, the slope of the line right at that point is equal to 1. Okay, so that is the reason that mathematicians have singled out this number e. So let's go through a few bullet points on your notes. So the number e is approximately equal to 2.71828, and it goes on forever, kind of like pi does. All right. E is very important for modeling things that occur in the natural world, especially things like population growth and radioactive decay. All right, so let's work a few examples. This is really very much going to be a calculator lecture where you're going to be using your calculator to answer questions. So the first one example says world population in millions is modeled by the function p of t. So p of t is equal to 2600 times e to the 0.018 t, where t is equal to the number of years after 1950. Okay, so when you see p of t, think of this as population. So that's big P. And t stands for with respect to time. So population with respect to time. Okay, so we want to estimate world population in 1970. So 20 years after 1950. So that means P of 20. T is equal to 20. So that's going to be 2600 times E to the 0.018 times 20. So let's put this in our calculator and we'll get an estimate of world population in 1970. Okay, so we've got, let me put it over here so you can see the model. So we've got 2600 times, and the E function is in blue on this TI-84. So hit second, and then E to the X is above the LN key. That's the natural log key. And you can see that it goes into a exponential right there. And we're going to fill in the exponent. And you don't have to, you let the calculator do the work for you. So you just type in 0.018 times 20. Okay, so all that's part of the exponent. We hit enter, and we get 3726.66. And that's in millions. Okay, that's our estimate. The actual population in 1970 is estimated at 3,700 million. So 3.7 billion. So that's pretty close. So that's a pretty good model. Okay, so let's estimate. So we're just going down your notes. World population in 1990. So what would be T in 1990? Well, T is number of years after 1950. So 1990 minus 1950 is 40 years. So we're going to be doing P of 40. So that's going to be 2600 times E to the 0.018, and we substitute 40 in for T. All right, so all we have to really do is go up here and edit. See if we can edit that. And I can arrow over to the 20 and type over with a 4. So I've got, all I did was edit the previous one and do 40, and I've got 5341.53. That's million, so that's 5.34 billion. And the actual, so that's what our model says, the actual in 1990 was 5,320 million. So again, this is a good model. Gives us a pretty good estimate of actual population. All right. So let's do one more. Let's look at 2010. So I'm going to erase the first two bullets there. So we'd estimate our population in 2010. All right, so in 2010, that's 60 years after 1950. So P of 60 would be 2600 E to the 0.018 times 60. So once again, we can go in and just edit our equation. I'll arrow over and type a 6 over that 4, hit enter, and I've got 7656.2. That's what our model estimates. The actual population in 2010 was 6.892 million. So 6.89 billion. So the model is not as good. So models have to be adjusted over time. Things change. Demographic tendencies changed between 1990 and 2010, and the world population grew at a slower pace. All right. So there you go. That's how you use E in your calculator and plug numbers in. And that's basically what you're going to be doing on this homework. So I've got one more example to look at. If you'll turn the page, up at the top, says a certain type of bacteria grows according to the function P of t is equal to 100 e to the 0.2728 t, where P is the number of bacteria present, T is elapsed time in hours. Find the number of bacteria present after 5 hours. Okay, so our model is P of t is equal to 100 e to the 0.2728 t. After 5 hours, we want to find how many bacteria after 5 hours, so that's P of 5. So that's going to be 100 e to the 0.2728 times 5. All right, so let's clear out our previous one. We've got 100 times second function, hit the natural log key, so e 0.2728, and then times 5. And we have 391.2. We'll just round that since you don't have a 0.2 of a bacteria. We'll round that to 391 bacteria present after 5 hours because it's exponential. That's going to grow a lot as time goes on. Okay, so your homework is worksheet 4.4, and if we want to look at that real quick, it's really just those types of problems. You read through. I do want you to write out the numbers that you're placing into your calculator, just like we did right here, P of 5. I want to see that every time, and then you can put it in your calculator and answer it. Okay, so really it's just a matter of reading through and putting the numbers in your calculator in the right spot. And let's see how well you do on that one. And I will talk to you on the next video.